Hi guys, today we're going to learn about optimization. What does optimization problem mean? The problem of determining a minimum or maximum value is going to be an optimization problem. In an optimization problem, the primary equation is one that gives you a formula for the quantity to be optimized. The feasible domain of a function is going to consist of the values of x that make sense in the context of the problem. Then you're going to have a secondary equation that it's going to be used to rewrite your primary equation as a function of one and only one variable. Okay, so we're going to list the steps for solving optimization problems. Okay, so you're going to identify all the given quantities and quantities to be determined. If possible, make a sketch. After that, you're going to write the primary equation for the quantity that is to be maximized or minimized. After that, we're going to reduce the primary equation to one having a single independent variable. This may involve the manipulation of a secondary equation relating the independent variables of the primary equation. This one will help you a lot, okay? This will make your equation much easier. After that, you are going to determine the feasible domain of the primary equation. This means to determine the values for which the stated problem makes sense. And last but not least, we're going to determine the desired maximum or minimum value by the calculus techniques discussed in previous sections. This means the extreme value theorem or candidate test or the first derivative test. Those are the two basically resources that we have from previous lessons that we're going to keep using. Okay, so let's read this problem, and you are going to see that it's not that bad. Okay, so we have a closed rectangular box with a square base is to be built so that its volume is 72 centimeters to the power of 3. If the bottom of the box costs 60 cents per square centimeter, the sides cost 35 cents per square centimeter, and the top costs 30 cents per square centimeter, we need to find the dimensions and the cost of the least expensive box. We need to justify our answer. So, as we were mentioning, the first thing that we are going to do is we are going to draw our situation. Here you are going to have pretty much a square at the top. Okay, so you have a situation like this. Okay, you know that this is a square. Okay, after that, you don't know if the front faces are squares. Okay, so I'm going to make it a little bit longer. Okay, but at the bottom you again have the same square that you have at top. Okay, so these parts that you see, they are congruent, and then this is congruent to this one and to this one. Okay, but we don't know if this one is congruent to this one. Okay, so for the sake of this problem, I'm going to call this side. Okay, and this is the height. Okay, so in case that you're wondering, the side is going to be equal to the side of the square. Okay, and this one is going to be in centimeters. Okay, if you're wondering what's h is going to be the height, okay, of the basically the rectangle. Okay, or front face. Okay, front face, and that one is also in centimeters. Okay, so you have that. Okay, now what's next? You realize that I give you that the volume is going to be equal to 72, but you know that the volume, following this idea, is going to be side squared times h, which is 72 centimeters cubed. Okay, so that's going to be my secondary equation. How do I know that? Because I know that my goal from this problem is to find the dimensions and make the cost the least expensive. So my cost equation is going to be my primary equation. Now, how can I create the cost equation? You know that the cost of each face is going to be different. Well, of three of the faces. Okay, so we have that the bottom, okay, so this face is going to cost 60 cents. So you know that that one is 60 cents per square centimeter. This means that the area of this guy, you know that it's s square. Okay, then you have plus, you are going to have the faces around this person, and you know that those faces are similar, are actually congruent, and it's 0.35, but you have 4 faces. okay? This one, the back one, and the one that it's here that you don't see, okay? And that one, the area of that face is going to be S times H. Last but not least, we have the top face that we have over here. That top face, according to the problem, it's basically 30 cents, okay, 0.3, okay? And that one you only have one, the top, okay? And that one you know that the area is S square, okay, because that one is a square as well, okay? So the only rectangles that you have are the 4 that you have over here, okay? So this equation that you have over here is in terms of S and H, okay, because you have a H here, okay? So I would like this cost equation to have only one variable, okay? So since I have a lot of S here, S, I'm going to convert the H in terms of S. Where? From here, the secondary equation. That's why I'm going to use this equation. So from that, you have that H is going to be equal to 72 divided by S squared. Therefore, what are you going to do? You are going to have your cost equation with respect to S, leave this guy the same, so you have 0.6 S squared, plus you have that 0.35 times 4, that's 1.4, okay? You have the S, but you are going to replace the H for 72 divided by S squared, okay? Then you put the plus 0.3 S squared, okay? So far we have everything with respect to S, but over here I really want to see if I can combine like terms or simplify my equation, because I know that I'm going to take the derivative, right? So you recognize that this guy and this guy, they are like terms. So that's really good, right? Because you have that it's 0.9 S squared. In addition to that, you recognize that this S cancels with this one, and then I can multiply 72 times 1.4, which gives you 100.8, okay? And then that's going to be divided by S. So this is your cost equation. Honestly, it doesn't look that bad, okay? So that one, it's pretty easy to take the derivative of. So we take the derivative C prime of S is going to be equal to 1.8 S plus, well, actually not plus, negative, because you want the derivative, right? So it's going to be minus 100.8 divided by S squared. If you're wondering how I got this one, you know that this one I can pass it as S to the power of negative 1 and then take the derivative, and that's what I did here using the power rule. As you can imagine, over here I want my critical number, so I want to equalize this to 0, having 1.8 S equals 100.8 divided by S squared. After that, what I'm going to do, I'm going to manipulate my S, so I have S cubed is equal to 100.8 divided by 1.8. So what you have is that S is going to be the cube root of 100.8 divided by 1.8. Okay, so this one, when I plug it in the calculator, let me show you what I got. I got that it's 3.8258. Okay, this is in centimeters. Okay, so what you have here is going to be your critical number. Okay, and now you're going to ask yourself, hey, do I have a closed interval so I can use the extreme value theorem? And the answer is no, I don't have a closed interval in this situation. Therefore, your best shot here is to use the first derivative test. So for the first derivative test, you need to be very careful, because when you have the derivative here, the 0 will not fly, because that will make undefine your situation here. Therefore, you have that it would be from 0 to that value. If you want to put it in decimal, go for it. Okay, to that value. Okay, to pretty much infinity. Okay, and then you would have that you are going to evaluate C prime there. Okay, here's your C prime. Okay, so I would select a value such as 1. If you have 1 there, that's going to be negative. If you select a number like 4 here, that's going to be positive. So by first derivative test, you know that this is a relative minimum, because C prime is changing from negative to positive there. Okay, so at this point, you're like, great. I'm going to plug my values in the calculator. So to find h, what are you going to do? To find h, what you're going to do is you're going to plug it here in this equation. So you're going to replace your s for the h, and that one will give you that s, that s is equal to this, and then the h is going to be equal to 4.9189, okay, and this is in centimeters. Similarly, you are going to plug the s into your cost equation. Specifically, I would plug it in this one. It's pretty easy that you just plug it here and here, the value that you have over here, okay, in your calculator. And I would have here in your calculator that it's 39.5205, and this is in dollars, okay? So this is in dollars, okay? We have pretty much all the situation, but we haven't justified our answer. So I'm going to grab another piece of paper so we can justify, okay? So what you have is that the least expensive box cost $39.52. If you want to put more decimal places, be my guest, okay? And the dimensions are in this situation is s is equal to 3.825 centimeters, and what was the other one? H is equal to 4.9189 centimeters, okay? What's your justification here? We know that C has a minimum at S equals 3.825 because C prime changes, okay, from negative to positive there, and that one is pretty much you are stating here your first derivative test, okay, and that comes from the table, okay? So that's what we have for this problem, and that's pretty much it. For this problem, what we have is we want to optimize the surface area of a cylinder that will hold 500 milliliters of water. When we got a circular top and bottom, you will have to use square pieces for the top and bottom and discard the scraps when you cut the circle. So at this point, you are like, what in the world is this? Okay, so I'm going to stop here and draw my situation. Okay, so you have a cylinder. Okay, so we have something like this. Okay, so you have a cylinder that looks like this. Okay, and what's the deal with the circular top and bottom? Okay, so we have square pieces. Okay, so please use your imagination for this one. Okay, we have a square piece here. That's a square apparently, and this one is a square. Okay, the same thing happens here. We have a square piece here and here. Okay, we're going to have a square piece there. Okay, for the top and bottom, and discard the scraps when you cut the circle. So we're going to discard pretty much all of this. Okay, so the extras. Okay, that's what we don't want. Okay, so we want to make it as small as possible, the pieces that we don't want. Okay, so what will the dimensions of the two sheets of aluminum need to be to minimize the surface area of a can that can hold 500 milliliters? Okay, we need to justify your answer, and then they give you the volume of the cylinder and the surface area of the cylinder. Great. Okay, so what's the deal here? Well, we have that the radius is going to be here. Okay, that's going to be R, and from here, let's say here to here, that's going to be your H. Okay, so the radius is going to be radius of circle. Okay, pretty much the top. Okay, or bottom. Okay, top, bottom. Okay, and that's going to be given in units. We don't have the units, so units. Okay, and then you have that the height is going to be the height, okay, of the cylinder. Okay, and that one is also going to be in units. Okay, so I don't have much there, units. Okay, so what's the deal here? Well, let's start with the information that it's given to us. The first thing that they gave you is that 500 milliliters, therefore you know that the volume, which is equal to pi r square h, is equal to 500. Okay, as you can suspect, since my question is to minimize the surface area, I know that this is going to be your main equation. This is a secondary equation. Okay, so let's do the surface area. The surface area of this situation, you know that from the formula that we have here, I know that it's basically my independent variables are r and h. So you have a situation like this, and let me just copy the formula so you know where I'm going and you can see all the steps here. Okay, so that's what we have, and you would recognize, everything has r's, so I want to change the h. Makes sense. Okay, so I want that h is equal to 500 divided by pi r squared. Okay, so what I'm going to do is I'm going to replace h over here for this one. Okay, so let's do it. So you have a surface area with respect only to r. So you have 2 pi r times 500 divided by pi r squared, close it, plus 2 pi r squared. So what you're going to do, you cancel the pi's, you cancel this r. Okay, so you combine here the situation, so you have that the surface area with respect to r is going to be equal to 1000, right, divided by r plus 2 pi r squared. Okay, and this equation actually, it doesn't look that intimidating. It looks pretty user-friendly. So I'm going to take the derivative of that situation. Okay, so you take the derivative with respect to r in this situation, you have that that's negative 1000 divided by r squared plus 4 pi r. Okay, so that's my derivative. I know that at this point I want my critical numbers, therefore I want to equalize this to 0. When you do that, you have that this is going to be 4 pi r is equal to 1000 r squared. Okay, after that, when we do the cross multiplication, or we pass this multiplying to the other side, however you want to call it, I have that r cubed is going to be equal to 1000 divided by 4 pi. You know that this is the same as saying 250 divided by pi. Therefore, what do you have here? I cube root both sides like on the previous problem, and you have that r is going to be equal to the cube root of 250 divided by pi. Okay, if you want to plug this in the calculator, this will give you the beautiful number of 4.30127 units. Okay, so you have that that's going to be the value of the radius. Okay, now what are you going to do? Again, you ask yourself, do we have a closed interval where we can like have a max or min or something like that, that we can test the extremes? And the reality of the situation is that we don't. Okay, so you are like, okay, I have the 0, but again, you see that the 0, it's game over here for the derivative and the original. Therefore, what you're going to do here is 0, comma, you put that number, the crazy number. Okay, if you want to even put this one here, you could. Okay, but I'm too lazy to write the whole thing. Okay, so you have this, and then you have to test the surface area prime. Okay, so you select, let's say, 1 again. So if you select 1, this is going to be very negative. This is going to be much smaller than this one, so obviously this is negative. If I put 100 here, this is going to be smaller, this is going to be bigger, therefore this is positive. This is again a relative minimum, as you can see. Okay, so what's the deal here? They are asking you, let's read the problem, what will the dimensions of the 2 sheets of aluminum need to be to minimize the surface area? Okay, so they are asking you not for R, they are asking you for this piece, right? Let's call it S. Okay, so let S be equal to the side. Okay, I'm going to call S the side of the what was it, the bottom discard, the aluminum square. Okay, the side of the aluminum square. Okay, so S is going to be equal to what? if this is S and this is R, you know that 2R is going to be S. Okay, so we know that S is equal to 2R, meaning S is going to be equal to 2 times, and I would put the cube root of 250 divided by pi. Okay, so what do you know here? Let's conclude. Okay, get ready to conclude now. Okay, so since S prime, okay, changes from negative to positive, okay, at what was it? R equals 4.301. Okay, we can conclude that SA has a minimum, okay, there. Okay. In addition to that, okay, this is how I'm going to justify my conclusion, right? The dimension, okay, dimensions, okay, of the aluminum piece, okay, are S equals to 2 times, if you want to put it like that so you don't confuse the cube root for another thing, it's equal to this, units long. This is the conclusion for your problem, okay? And that's it. Okay, so let me show you all the problem. Here you can see it, beautiful. So we actually answered the question, which it was the dimensions of the 2 sheets of aluminum. Okay, so hope you find this video helpful. Bye.